Hello, hello. Okay, seems everyone can hear. All right. So today the office hour will cover the problem set 12. This problem set contains a lot of questions. I'm trying to go through the whole problem set, but I'm not quite sure if we have enough time to do that. So if you have any specific questions, please ask after I finish these all problems. And if we really don't have time today, we will have another office hour tomorrow or later. So just prepare to post your problems on Piazza. And I believe your problems will be answered in the next office hour. I'm not quite sure if you already have the solution yet. But I'll just try to talk about details or general ideas to help you understand this chapter and all the problems. Okay, now let's start from the problem one. The condition is that all languages in this problem are over the alphabet sigma equals to the set of 0 and 1. That means every character will just be 0 or 1. So part A is that we want to construct a map reduction from A to B, where A is the set of X, where the size of X is larger than 10, and B is the set of machines where MX, where hearts whenever X contains a 1. That means if X contains a 1, then it hearts. So before I talk about this problem, I just suggest you to change your quality to 720 or the source, so that you can see all the nodes clearly. I'm not quite sure if the default setting will give you a clear screen, but just take care about that. Okay, so let's move back to the problem one, part A. What we need is a function f, which is a mapping reduction from A to B. And one more constraint is that f should be computable. So there can be actually many kinds of such functions. Here I just give you one idea of that. So clearly f should accept input x. If x, if the size is larger than 10, we output MA. Otherwise, output ML. So here MA means that it is a Turing machine which accepts every input. And ML means that it is a Turing machine which will loop on every input. So we need two constraints. That first one, F should be computable. This is clear here, right? Since no matter what X is, it will output something. See, if X, the size of X is larger than 10, it outputs this machine. And if the size of X is not larger than 10, it will output this machine. So it will always output something. Therefore, F is a computable function. Then we need to show that F is a mapping reduction from A to B. So there can be we need to show two things. The first thing is if X is in A, then Fx is in B. And the second thing is if X not in A, then Fx is not in B. We need to show both of them. Then we can say F is a mapping reduction from A to B. Okay, so for the first one, let's call it for part part 1. If X is in A, then we know that the size of X must be larger than 10. Right? This is definition. A is the set of X where its size is larger than 10. In this case, F outputs MA. Then, still according to the definition here, MA will accept all inputs, right? These all inputs include those inputs contains 1. Accepts all inputs, including those containing the 1. Therefore, it is in B, since B is the machine that hot whenever X contains a 1. In this case, MA will just hot whenever X contains a 1 because it hot for every input. So for part 2, if X is not in A, then the size of X is not larger than 10. So in this case, F outputs an L, which will always loop. Since it loops on every input, it will loop on those inputs which contain a 1. Therefore, it should not be in B, since it will not hot. So now we have proved both parts. Therefore, we can say that F is a mapping reduction from A to B. Right. The problem asks that we need the problem wants us to construct such a map reduction, and we have constructed in this way. So actually, this 10 is just a we can change this 10 to any other number, for example, 11, 100, anything. Or if we can change 10 to n, then we still we just need to make a small change here, and everything else goes will be the same. So the general idea is we do not need to care about the inputs which contains a one. We just need to care about every inputs, because all inputs will include those inputs which contain a one. This is how we do part A here. So similarly, when we go to part B, the general idea is similar. We still define such a function f will accept input x. But in this case, we see that A is the set where the size of x is 42. So if the size of x is 42, then output ML. Since this time we want something that loops forever, right? We have FL, and otherwise output MA. So these two things are still the same as the first part. MA is the machine which accepts every input, and ML is the machine which loops on every input. Now, similarly, we see that if x is in A, that means the size of x is 42, then fx will be the machine that loops on every input, including those containing a 0, thus it will be B. And if x is not in A, that means its size is not 42, thus we will output a machine which will house for every input. Clearly, that will not be in B, right? Since it does not loop forever. So we can still prove these two parts, and also similar to show that f is computable. In both cases, f will output something. So for same reason, or we can say similar reasons, f is a mapping reduction from A to B. So still the same if we change this 42 to some specific value n, we also need to make small change here, and everything else are the same. That's all for part one, problem one. I believe this one should be not very difficult, and I think you can understand it. Now let's move to problem two. Problem two, so HTM is the machine, is a set of machines which harps on every input, on some input epsilon, and we need to show that there is a mapping reduction from the HTM to L for the L defined as following these L's. So let's first consider about part A. So for this part, that's not what I want. Okay, so L is the set of machines where the length of LM is. Okay, so this is the only constraint on this L. So see that for this problem, we want to show that there is a mapping reduction from HTM to F. So still similar to problem one, we want to construct a function F. Construct a function F which accepts input M. Why the input is M? Because for both HTM and L, they are all sets of Turing machines. So F is a function which accepts input M, and it also needs to output some machine, right? Since L is also the set of machines. So for the input machine M, we just output a new machine. We call it NM. This is a machine which takes in input X and just run M epsilon. I just use small e here to replace the, because in the Word file I don't know how to type that epsilon symbol, and I just accept. This is definition of M. So F takes input M and output this machine NM. The M will be used here because we need to run M epsilon. Still, we need to show that F is computable, and F is a mapping reduction from HTM to F. Computable is easy, right? It always outputs something. To show that it is a mapping reduction, we still need to show that both parts. So for the first direction, we say if some M is in HTM, then according to the definition, oh wait a second. So we want the output of F, right? So the output of Fm will be Nm. This machine will accept all inputs and finally accept. Therefore, everyone can see this, right? Okay, so if M is in HTM, recall this definition. When we run this M epsilon, it will definitely half, right? This is the definition. So we will finally accept. But if it is not here, that means if M is not in HTM, that means M will not have on the input epsilon. So when we run, yeah, for NM, when we run M epsilon, it will just loop forever. Therefore, we will not. It is impossible for us to finally accept. Thus, NM will loop on every input. In this case, the LM will be 0, so it is not in air. Since in air, it will be at least 12. So generally, it's still similar to problem 1. This 12 is not that important. We just need to have two. We see one of them is infinity and one of them is 0. So if the 12 is replaced by any number larger than 0, for example, 1, 2, 3, 4, we can still use the same function f here to get the same result. Wait a second. The notation is off. Which notation? For the second problem, you ask why Lm why it is in L, because it is infinity, and clearly it is at least 12, right? Infinity it means that it is really large. And if it's 0, then it is not in L because 0 is smaller than 12. I can see. Oh, I fixed it. Okay, thank you. Let's move to part B. In this case, let's really that Lm equals to infinity. So can you see the similarity between part B and part A? See, using the same function f here, there can be only two cases. One of them is it is infinity, and one of them is 0. So suppose we use exactly the same function f here. What we will have? We will still have that if m is in HTM, then the length will be infinity. So it will be in L, since L is those machines with a length infinity. And if it is not in HTM, it will be 0, so it's not in L. So the exactly same function part A will still work in part B, right? Since we can change this 12 to any positive number. Now let's go to part C. So for part C, the constraint is that L is the set of machines which accept some palindrome. So can you see the similarity and difference between C and A? You see, for parts, if we use this function f, we know that if m is in HTM, then it will accept something, right? Actually, it will accept everything, since when we run m epsilon, it will finally halt. But if it is not in HTM, then it loops forever, so we accept nothing. Therefore, if we use the exactly same function in part A, we will see that if M is in HTM, then the NM will accept everything, including those which accept some palindrome. And if M is not in HTM, then it will accept nothing, right? So that will not be in L. So we can still use the same function in part A. Understand? So NM, if NM is a machine that accepts everything, then it clearly accepts some palindrome, so it will be in L. For part D, so the language of M is 0, 1, 2, 2. Okay. This is the constraint. Clearly, the same function f cannot be used here because there is a more strictly constraint here. The language of M must be in the form of this one. But the general idea is still similar. We still design f as a function that accepts input m and output some nm, where nm will be the machine that takes on any input x, just to run m epsilon. But in this case, even if m epsilon does not loop forever, we don't directly accept, but add another constraint here. If x is in the form of accept, otherwise reject. Okay, see the main part here? But still, f is computable. We don't need to talk too much about that. In this case, M is in HTM. Then we know that the NM will taking an input X and run M epsilon, and it will clearly hot. But after that, wait a second. Yes. So so these two parts actually meaningless, right? So if M is in HTM, then FM which equals to NM is the machine which accepts only accepts input in form in this form, right? it will accept all the x which are in this form and reject other inputs. So since NM is the machine that accepts only this form inputs, it will be in L. Because L is the sets of machines that the language is in this form. On the other hand, if M is not in HTM, and for this part, it is actually the same as the part A, B, and C. And will loop forever. Therefore, this machine cannot be in air because it will never hunt. So, any question about part D? Since I believe part A, B, C should be easy for you to understand. It has been half an hour, so we need to speed up a little bit. Now we move to problem 3. Show that a language error is decidable if and only if error is a mapping reducible to a finite language. So there are still two directions to prove since we have if and only if. So the first direction. We suppose error decidable. Then just follow the most common idea. Since error is decidable, there must be a decider for error, and that we say M is a decider for error. In this case, what we need to show. Suppose error is decidable, we just need to show error is mapping reducible to a finite language, right? So we still need to construct a function f, which is a mapping reduction from error to some finite language. The finite language can be anything. So let's speed up a little bit. So let f be a function. The input is x, and it will run mx. If accept something, we say, for example, 1, if rejected. We still output 1. Now, in this case, we use 1 as the finite language. Right. This is the finite language 1. Now f is a mapping reduction from error to this finite language 1. Can you see that? So if something is in L, since M is the decider, if it accepts or rejects, that means X is in L, then Fx is 1. Similarly, if X is not in L, then both cases will not happen. So Fx will not be 1. Oh, I'm sorry. Actually, output 0 maybe. This is for the first direction. For second direction, we suppose there exists a f mapping reduction from L to A, where A is finite language. Oh, what do you have? A is a finite. Is finite. This implies that A is decidable. You should understand this, right? Since A is finite, we can always construct a machine that checks every element of A, right? Since it's finite, it has finite elements. We just need to use the machine to check if the input matches any of the elements. We check all the elements to see if the input matches one of them. Now, then we know if it accepts or rejects. So A is decidable. Therefore, we can have another Turing machine. We say N. Input X. At Y equals to Fx from My. If accepts, accept. If My accepts, we accept. Then N accepts. Rejects. Reject. Then we can see this Turing machine N should be a decider for L. Right? It should be clear. Because M is a decider for A, so N will accept or rejects every input. Since since if X is in L, then Y is in A. Since Y equals to FA. If X is in L, then Y is in A. If X is not in L, then Y is not in A. Right? So if My accepts, N accepts. If My rejects, N rejects. Then we know N is the decider for L, which means that L is decidable. So these are the proof of the two directions. Maybe the first one is more simple. I'm sorry, I didn't see your comments before. Let me check it now. Where does NM say it will loop? Part D. For question 2, NM is a machine that takes an input and the wrong M epsilon before it accepts or rejects, right? If we say that HTM is the set of machines that has our input epsilon. I'm sorry. So if it is not in HTM, that means it will not have only input epsilon. So in this part, it will loop forever. So we do not need to say do not need to define that and then will loop forever, because in this part, when we run M itself, it will loop if M is not in HTM. This is for that question. For pass recording is 0, no. It is not 0, 1. What we do is to map L to the finite language 1. That means if something is in air, if a machine is in air, then the output is in will be 1. In the other case, if M is not in air, then the output is not 1. It can be everything, right? It doesn't need to be 0. It can be everything other than 1. We just need to show that these two have the mapping relationship. So the language is still 1. Okay, someone actually answers your question. Good. Now let's go to question 4. Show that if A is recognizable and A is mapping reducible to the complement of A, maybe we say it's A bar, then A is decidable. For this one, this question is not very hard, but we need to know those concepts and theories. The first one is it's a little bit difficult to type the R here. Okay. It's fairly challenging for me to use the paint. So the lemma one is if there is a mapping reduction from L to L prime. Oh, I'm sorry. So there is a mapping reduction from L to L prime if and only if there is a mapping reduction from L bar to L prime bar. And the lemma 2 is if there is a mapping reduction from L to L prime and the L prime is recognizable, then L is also recognizable. So for this problem, so everyone see this? Going to right here. So according to the problem itself, A is mapping reducible to A complete or A bar. So we do have we have this one. Then by lemma 1, let's say A bar is the L prime and A is L. Then since we do have this, then we can have that this one is just A, right? So we have this conclusion. And also by lemma 2, we know that A is recognizable. And A bar is mapping reducible to A. Therefore, A bar is recognizable. Finally, since A and A bar are both recognizable, we know that A is decidable. These are all concepts, basic concepts, lemmas, and theorems. There is not much technical here. You only need to know these things, and you will be able to solve this one. It is nearly impossible to cover all problems here. We will skip question 5. You can ask tomorrow. Since question 5 will take a lot of time here. Let's move to question 6. So R is a set of machines that the intersection of RM and the 0, 1 is just 1. I mean, the size is just 1. That means for the machine R, it will accept only string 0 or string 1. But since the size is 1, it cannot accept both. So part A, what does Rice theorem about R? So seems that someone asks about the Rice theorem. Rice theorem cannot tell you if some language is decidable, but it will prove that some language is undecidable under specific conditions. The most important thing is the trivial or non-trivial property. So if you want to show that, so here when you see, this is a tip. So in the homework or in the exams, while you see the question is what does Rice theorem say about something, or what can you get from the Rice theorem? In most time, the conclusion will be this language is undecidable, right? Because the Rice theorem is really efficient for you to prove some languages that is undecidable. So here, Rice theorem tells us that L is undecidable. So why? We first see that we first need to show that L is a language, right? The Rice theorem is only about the language, but this one is really clear. Suppose for the two machines M and M prime, Lm equals to L M prime. Here's a little bit. Let's see, just a sec. You can see this. This is just a basic definition or basic idea. So this one is not very important here. The most important thing is you need to show L is non-trivial. Give me 1 second. So if we say that some language is non-trivial, it means either exists some EM that recognize. Okay. This is the definition of non-trivial. Here we need to show that it is non-trivial. That means we need to find two machines that one of them recognize a language in L and one of them recognize a language not in L. M1, let's say M1 is a machine accepts just 0, right? Clearly M1 is in L. M1 is in L because it will accept only the string 0. So if we get the intersection of with the language 0, 1, the size will only be 1. And let's say M2 is a training machine that rejects everything. Then clearly M2 is learning L, right? Because the machine in L will accept either the string 0 or string 1, but this M2 accepts none of them. Therefore, we can find these two machines. So with the right theorem, L is non-trivial. There is a set of languages. Therefore, it is undecidable. Now for part B, still we have HTM here, and we need to show HTM is mapping reducible to L. You should be familiar with such problems. You just need to define still you need to define your function f accept x and still the HTM one is familiar, right? We are familiar with it. We just again we run m epsilon and this part, the run m epsilon part, will finally decide if it will terminate or not. It will loop forever or it will finally halt. And if x equals to 0, we just accept. Otherwise, reject. If it's computable, and if m is in HTM, then we will output something. Oh, I'm sorry for that. Right? This is similar in this one. So for the m in HTM, f will output some machine that accepts only 0. If m is not, since it accepts only 0, it is in L. Right? L is the set of machines that accepts either 0 or 1. Since this one accepts 0 but not 1, it meets the requirement, so it is in L. In other cases, if M is not in HTM, it will loop forever, and M will loop forever, thus it cannot be L. For part C, we need to show that HTM is reducible to L, the complement of L. I just give you a conclusion, and you can think about why it is correct. So still a function f accepts the a machine and output a machine which accept input x. But this time, if x equals to 0, wrong. And epsilon. Otherwise, we just accept. Otherwise, yes, otherwise we just accept. Then, in the case that x equals to 0, this machine will always will either accept or loop forever, right? You just need to think about what L bar is, then you know why this is correct. So think about okay. So move to the part D. Is L recognizable? And what about L bar? Why or why not? Conclusion. They are neither of them are recognizable. For this part, you can go back to question 4, right? You can use the contradiction to prove it. What we know is HTM is undecidable, but recognizable. Since we do have HTM is undecidable but recognizable, we know that the complement of HTM is not recognizable. Since if they are both recognizable, then HTM will be decidable. This is just this is kind of contradiction. Now, part B and part C, B and C gives us that both L and L bar are reducible. I'm sorry. Part B proves that HTM is reducible to L bar, to L. And this implies that RHTM yeah. Do you still remember this lemma? Lemma 1. And since bar HTM is not recognizable, area is not recognizable. See, this is a contradiction lemma 2 if you go back from M prime to A. Because if bar area is recognizable, then we know this is recognizable, and we do have this, then L must be recognizable. The area is actually the bar HTM here, but we know by contradiction bar HTM is not recognizable, so bar area is not recognizable. For the same reason, you can prove using part C. This is from part B. You can prove from part C that L itself is not recognizable. Now we go to question 7. I spend a little bit more time to talk about question 7 and maybe question 8. There's 3 parts of that question 7. The error is defined in this way. It will accept finite many words because you see smaller than infinite, it means accept finitely many words. And to show error is undecidable, again we use Rice's theorem. We need to show error is non-trivial. We decide 2 machines. M1 accepts everything. M2 rejects everything. Right. So M1 is in L and M2 is not. Then property of sandwich. Similar to the question 6, you just need to show this. It is clear. You can just write it here. If L equals to L M prime, then size of Lm is smaller than infinity, if and only if the Lm prime size is less than infinity. That is really easy. So for part B, we need to show if error is recognizable or not. If so, we describe a Turing machine recognize it, and if not, give a proof. Error is not recognizable. Again, we use HTM. This one is really useful here. So we just need to prove that HM is reducible, mapping reducible to RM, or you can prove that HTM bar is mapping reducible to M. These two are equivalent by lemma 1. So if you do have this, you can prove the property here and the similar strategy here to show that error is not recognizable. You can try this yourselves. Really similar to part D here. But you need to design the function, which is the mapping reduction from HTM to bar M. Actually, I can give you what it is. But still, we need to use NMC. I don't write all of them, but just describe this machine. Input X. And rational. Set. Right? We can prove this. And for part C, we need to show if it is co-recognizable. Now, you can see that the language is co-recognizable if its complement is recognizable. So actually, we just what we want to show is whether L bar is recognizable. So the conclusion is error bar is not recognizable. So for really similar, we need to show this. Right? If you have this, we can show that error bar is not recognizable, and therefore error is not co-recognizable. This one is actually more difficult. You can ask if you so question 7 part C. You can try to work on this yourself, and if you cannot finish this, you can ask tomorrow. Because as I think this is the most difficult part of question 7. And then question 8. Wait a second, I see the question. For question 6, error bar be recognizable? We do have the Turing machine goes through everything that is not during. Okay. Since you do have this problem, part C, what we need to show is error bar. So what is this? This is a set of machines that this is what an error bar is, right? So in part C, we use this error bar to get the conclusion that HTM is mapping reducible to it. And finally, in part D, we use odd concepts here to show it is not recognizable. So I'm not quite sure what the question is. You say you have a Turing machine goes through everything that is not 0 and 1, so it is recognizable? It is not the definition. So recognizable doesn't mean it accepts everything. It means that there is a machine that will pattern accept only the strings in this language. There is nothing. What do you mean by goes through everything that is not 0, 1? You mean if it is not 0 and 1, then they accept? M just need to either 1 accept 0 and 1. I'm sorry, I'm a little bit confusing. I'm a little bit confused. So what if you want to say Airbar is recognizable, you need to give me a Turing machine which will part and accept only the strings in Airbar, Airbar including the strings that intersect the size to. It can accept 2 of them or none of them. How about this? We actually don't have too much time here. Let me finish question 8. Then I will check if I do have time for this for your problem. And if not, you can post on Piazza, post on just under question 6, and I'll take my time to solve your problem. Is that okay? Okay, don't worry. We may go back if we do have time. Let's finish question 8. Question 8, part A, prove that if the 2 languages L1 and L2 are recognizable, then the union of them is also recognizable. So we know that L1 and L2 are both recognizable, so we define M1 be the recognizer. I mean, M1 is recognizer for L1, M2 is the recognizer for L2. And what we need to do here, yeah, we need to show that the union is recognizable. So we need to find the recognizer for the union. So we construct this one for the input X. So initialize I equals to 1, while I is larger than 0, run M1X for I steps. If steps anytime, similarly, so here while I is larger than 0 is actually you can change it. For example, while 1 equals to 1 or while 2. So we just need to do this forever until it hard to accept. Now we need to show that M is a recognizer for this is actually very simple. So if X is in L1 union L2, then either X is in L1 or X is in L2, or both. Right? So if X is in L1, then there exists and similarly, if X is in L2, then it exists some K such that M2X accepts after K steps. So J and K are both just a finite positive number. Therefore, for this machine, suppose J and K, X is only in L1, then when I equals to J, we know that M1X will accept this X. Thus, here, it will terminate and accept. So if X is only in L2, we know that while I equals to K, and here, the machine will terminate and accept. If X is both in L1 and L2, for the smaller one of J and K, for example, let's say J is smaller than K, then instead J M1 will accept X, which means the machine M will terminate and accept. Therefore, M is a recognizer for the union of L1 and L2. And for part B, we need to show that the union of infinitely many recognizable languages is recognizable. We can just use the inductive argument that by part A, the unions of two recognizable languages is recognizable. So for the basic case, the union of two recognizable. Is recognizable. And for the inductive step, suppose union of I will always say K recognizable. Is recognizable. And the union of K plus 1 is actually the union of A and B, where B is recognizable and A is the union of K recognizable, which is also recognizable. So it is not formal to write in this way, but you just need to understand. So for part C, it asks that is it true that the union of countable many recognizable languages is recognizable? By the way, for part B, we do have the constraint finitely here. That's why we can use K to imply K plus 1, since these are both finite positive integers. And for part C, okay, the conclusion is it is not true. And you can use the example HTML bar, the complement of HTML. You can show that you can say that L equals to the complement of HTML, and you can show that L is a countable set. It is a countable union of languages, and each of the languages is recognizable, but the L itself is not recognizable. So you can find question A, part C yourself. Ask if you have question. So you can ask tomorrow if you cannot finish this part. So you can use the example HTML bar, and you can use other examples just as you want. What you want to show is the example language is a countable set, but it is not recognizable. We don't have time for question 9 and for question 6. One more question. Can we run M1 and M2 one step at a time instead of run one step check, two steps check? Okay, so what do you mean is each time we run M1 once and M2 once, and if both of them don't accept, then we run M1 once more and M2 once more, right? That's a good idea, but here since we only need to finish, we just need to terminate in finitely many steps. This one is looks better because it is more continuous, right? We just write for I steps, run M2 for I steps. Your idea sounds also good. But I would still suggest to you to do it in this way for no reason. You can ask if your more people will agree with your idea of the other, maybe. And loops for empty string. HTML bar here is the hot HTML bar, right? Yes. At E and well, any language is a countable. Give me a second. That's a good question. I think about it. Give me 1 minute. Okay, for this one, I asked the professor, since for this countable, I need to make sure about this one. I'm sorry for that. I will ask other TAs and professor to see if we can give a more clear definition of the word countable and the word singleton. We will tell you about all of this tomorrow. And if you are still not satisfied with the answer, you can ask from Piazza. Is that okay? Since I think I will do that just after this office hour. I'm pretty sure you will get a good result tomorrow. Okay, so the two questions about 6 and 8, right? So you do have problems about 8, and I actually have a little bit confused about this one. And for problem 6, you think that you can find the recognizer for the L bar. For that one, I'm pretty sure that L bar is not recognizable, but you can write the recognizer you think which is correct on Piazza, and all students and TAs will discuss and tell you whether that is, why that is uh, not not good enough. Okay, that's all for today's office hour, and I'll go back and chat with other TAs to see if we can solve your problems tomorrow. Hope you can have a good time today and tomorrow, and maybe on exam 4. See you guys.